20,000 lives were lost in the year 2011 during a catastrophic geological event that forever changed the approach to coastal safety. Why was a wall stretching nearly 250 miles along the eastern coastline deemed the only viable solution? It seems simple to block water with concrete, but in reality, the scale of a 50-foot tsunami involves kinetic forces that can crush standard architectural structures like glass. This massive engineering project was born from the shock of seeing hundreds of thousands of homes swept away by the ocean in a single day. One can notice how the construction site resembles a coordinated industrial theater where every movement is calculated. The process of building such a colossal barrier requires the mobilization of tens of thousands of engineers working in shifts around the clock. Giant excavators and specialized cranes move with the hiss of heavy hydraulics to position reinforced steel frames. It is visible how the metal lays in an even layer within the wooden molds before the pouring begins. The process is only gaining momentum as the foundation must reach deep into the coastal bedrock to prevent the wall from being toppled by the sheer weight of millions of tons of seawater. Precision is the primary requirement for every single segment of this concrete fortification. Because any structural gap or material weakness could lead to a total breach under the pressure of a 50-foot wave, every millimeter is calibrated by laser sensors and automated surveying equipment. But this is just the beginning of the technical challenge. World-class machines rotate ceaselessly to mix high-strength concrete that must resist the corrosive nature of salt and the violent impact of debris. It only looks obvious that a wall of this height would be sufficient for any future disaster. Yet the question of whether this concrete Great Wall can truly protect Japan from future tsunamis remains at the center of global engineering debates. The equipment gradually completes one section, moving the heavy shuttering systems to the next position along the coast. One can notice the dust settling in slow clouds as the heavy trucks transport thousands of tons of material to the shoreline. The transition to the next level of coastal defense involves not just height, but the integration of floodgates and sensors that react with millisecond delays. Thus, the massive structure reaches its final height, standing as a silent sentinel against the Pacific Ocean. This concludes one of the most significant phases of Japan's modern industrial mobilization. 4 massive tectonic plates converge directly beneath the Japanese archipelago, creating one of the most volatile geological junctions on the planet. This collision zone acts as a persistent engine of seismic activity where the Earth's crust grinds and slips without pause. Over 500 earthquakes are recorded annually in this specific region. Why is the northeastern coast of Japan forced to exist under a constant state of high-alert surveillance? Surface stability is merely an illusion in this geography. But in reality, the proximity to these shifting plates means the threat of a sudden displacement of the seabed is a daily statistical probability. The process is only gaining momentum. When these immense plates shift beneath the ocean floor, the seabed can rise or sink by several meters within a few seconds. This sudden vertical deformation displaces the entire water column above it. One can notice how huge walls of water are pushed upward, forming tsunami waves dozens of feet high. These waves do not merely drift toward the shore. They accelerate with the kinetic energy of millions of tons of water. At first glance, the ocean appears calm, but in reality, the pressure building behind the wavefront is immense. Residents of small coastal towns once relied on red alert warnings transmitted over loudspeakers to trigger immediate uphill evacuations. The earthquake on March 11, 2011, became the ultimate technical stress test for these human and mechanical systems. A magnitude 9.0 earthquake ruptured more than 300 miles of a tectonic plate boundary under the Pacific Ocean. The result was a tsunami nearly 50 feet high. It is visible how the water overwhelmed every defense Japan had previously engineered. This event led to the loss of more than 20,000 lives and the total destruction of over 120,000 homes. Everything only gets more complicated when critical infrastructure is involved. The wave triggered a major crisis at the Fukushima nuclear power plant after overwhelming the existing defenses. Old seawalls were designed to withstand waves of only 26 feet, a height that proved insufficient against the Pacific. Japan realized that while the earthquake initiates the event, the tsunami serves as the primary agent of destruction. Consequently, the nation began a massive construction project spanning nearly 250 miles of coastline. It does not end at this stage. The new concrete barriers stand between 45 and 50 feet tall. Their foundations are not superficial, plunging 80 feet deep into the ground to ensure stability against the lateral force of incoming water. More than $12 billion were invested into this infrastructure and the modernization of emergency alerts. These walls are engineered to buy precious minutes for evacuation rather than simply blocking the ocean. The equipment gradually transforms the landscape into a fortified zone. The process is a technical response to a recurring geological phenomenon. Thus, the defensive chain is completed to prevent a repetition of the 2011 disaster. 14 years of accumulated seismic and hydrological data serve as the absolute starting point for the construction of Japan's massive defensive seawall. Why did engineers spend thousands of hours conducting laboratory research before a single cubic meter of concrete was poured? It would seem that simply building a taller barrier would suffice, but without precise simulation of the 2011 disaster, the structural integrity of a wall under the pressure of millions of tons of water remains an unpredictable variable. Laboratory technicians meticulously recreated the hydraulic forces of the historic tsunami within specialized artificial wave tanks. It is visible how scaled-down models of coastal settlements are subjected to high-velocity water surges to study the exact mechanics of how waves hit and overtop a vertical surface. The process is only gaining momentum. One can notice the systematic adjustments made to the thickness, height, and slope of the barriers after every recorded failure in the tank. Only when the digital and physical models demonstrated the highest possible performance did the engineering teams finally lock in the definitive structural design. It seems simple to calculate the resistance of a wall, but in reality, the interaction between surging seawater and a fixed concrete mass requires calculating the precise angle of a trapezoid base to disperse kinetic energy. 39 to 49 feet is the final height of the wall above the ground level. At first glance, this height is the most critical factor, but the true stability lies beneath the surface where the foundation piles are driven 65 to 82 feet deep into the earth. Everything only gets more complicated when considering the internal structure of these giant segments. Because a simple concrete block would shatter under the impact, a reinforced steel core is integrated into the center of the trapezoid. One can notice how the wide base provides a low center of gravity, preventing the structure from being pushed over or undermined when the water exceeds the crest. The metal and concrete composite becomes a singular heavy monolith capable of withstanding the impact of an extreme tsunami. This concludes the engineering phase, allowing the transition to the physical assembly of the barrier along the coastline. 400 kilometers. This is the total distance the massive barrier covers as it stretches along the Tohoku coastline in northeastern Japan. This region bore the primary impact of the 2011 tsunami, and the defense line now extends without interruption through the prefectures of Aomori, Iwate, Miyagi, and Fukushima. Why was such an expansive and unified route chosen for the project? It represents the longest and most cohesive coastal defense system in the history of Japan, requiring a singular path to ensure no gaps remain for incoming water. Once the exact coordinates of the route were established, crews initiated the clearing of the landscape. They dismantled damaged infrastructure, removed remnants of old houses, and redirected power lines and pipelines. Preparation occurred on a massive scale. It is visible how workers established material yards and crane platforms while constructing concrete mixing stations and temporary drainage systems. This infrastructure allowed the work to proceed even through the heavy rainfall of the rainy season. At first glance, the coastline seems ready for heavy loads, but in reality, much of the Tohoku region consists of weak, sandy soil that cannot support immense weight. But this is just the beginning. Engineers conducted detailed geological surveys by drilling deep into the coastal strata to determine the necessary reinforcement. They drove steel or concrete piles deep into the earth and added layers of crushed stone and compacted sand to stabilize the surface. This creates a solid foundation capable of supporting a wall tens of meters tall without the risk of sinking or sliding. One can notice how excavators then began carving out massive foundation pits, some of which reach a depth of more than 20 meters. Near the shoreline, crews constructed temporary cofferdams to prevent seawater from flooding the active work zones. The process is only gaining momentum. After the pits were cleared, a base layer of concrete was poured to provide a level starting point. Workers then lowered dense steel reinforcement cages and large foundation blocks into the excavations. This resulted in an extremely heavy and wide-foot design specifically to prevent the wall from being pushed over by the kinetic energy of powerful waves. Above these foundations, the assembly of tall, thick rebar cages began, following the optimized specifications developed in laboratories. Formwork was positioned around the steel skeletons, and liquid concrete was pumped into the mold section by section. Each block, often measuring several dozen meters in length, underwent a strict cycle of pouring, curing, and inspection. These individual segments were then connected to one another to form a single, continuous barrier along the Pacific. It is visible how the camera glides along the ocean-facing side, where crews installed energy-dissipating blocks like tetrapods and delos. These concrete units were stacked in multiple layers at the base to shatter the force of the waves before they could strike the main structure. Everything only gets more complicated further on. Certain sections of the wall feature stepped faces or sloped surfaces to reduce the height of water surges. On the landward side, engineers added soil and crushed rock along with drainage channels to prevent rainwater from pooling behind the barrier. One can notice how many stretches now include a walkway or an inspection road on the summit. In several towns, the seawall serves a dual purpose by functioning as part of the local roadway system. Railings and safety ladders were installed to provide public access, marking the completion of the general construction principle. Because the project spans nearly 400 kilometers, each specific site required minor adjustments based on terrain and coastal depth. These variations were subtle and did not alter the fundamental structural integrity of the tsunami barrier. In areas requiring extreme impact resistance, crews added an armor layer of interlocking precast concrete panels to the outer surface. These heavy tiles were lifted into place by cranes and arranged in tight, uniform patterns to combat erosion. The transition to the next level of complexity occurs in busy port cities like Iwaki. How do ships navigate through such a massive, solid barrier? In these locations, Japanese engineers integrated specialized entry points to maintain marine traffic. One can notice the top-down tsunami gates, where massive steel panels are suspended between two high concrete towers. These panels are operated by hydraulic motors and complex pulley systems that can drop the gate in seconds during an emergency. This seals the harbor entrance like a vertical steel wall. In other ports, the solution involves a bottom-up rising gate that remains hidden. Under normal conditions, the entire structure lies flat on the seafloor to allow ships to pass without obstruction. When a tsunami warning is issued, a hydraulic system lifts the gate from the seabed and locks it into the sidewalls. This design is particularly effective for areas where overhead towers are not feasible, allowing 24-hour traffic. Because these gates reside permanently in a marine environment, they are built from highly corrosion-resistant steel with fully sealed hinges. The molten stream of engineering precision ensures the system remains operational despite constant pressure from sand and salt. The defense line stands complete, ready to face the forces of the ocean. The material has been placed, and the transformation of the coastline has reached its finished state. 400 kilometers is the total length of the continuous coastal defense system stretching along the Tohoku coastline. Why was such a massive scale necessary for a single engineering project? While a standard barrier might protect a small harbor, only a unified wall of this magnitude could serve as Japan's primary shield against the Pacific. This structure now stands as the largest continuous coastal defense system ever constructed in the history of the nation. $12 billion were allocated to bring this defensive vision to reality. The process is only gaining momentum. Over 30,000 engineers, geotechnical specialists, and laborers converged on the coastline to manage the immense workload. One can notice how the landscape transformed as thousands of heavy-duty machines operated without pause for a duration of 7 years. Construction occurred across hundreds of wall sections simultaneously to meet the strict timeline. It seems simple to build a wall, but in reality, every segment demanded a unique engineering approach based on the specific local terrain. Geotechnical teams performed foundation treatments and reinforced concrete structures with surgical precision to ensure stability. Transition to the next level. Simulations conducted after completion demonstrate that the seawall can reduce the impact forces of a tsunami by 30 to 50%. Such a reduction provides local residents with several additional life-saving minutes during an emergency evacuation. This window of time is sufficient to protect tens of thousands of people during a level 1 tsunami event. Fishing ports, coastal roads, and residential districts that were previously destroyed now sit behind this concrete barrier. The equipment used in the reconstruction has moved on, but the protection remains to mitigate the risk of catastrophic damage from major waves. Everything only gets more complicated when calculating for larger disasters. But this 400-kilometer barrier is not a total solution for every possible oceanic threat. It serves as the final line of defense for the country, providing a calculated level of confidence against the most devastating natural forces on the planet. The project concludes this phase, leaving a transformed coastline in its wake. Thus ends one of the most significant chapters in modern Japanese coastal engineering. 100 meters below the surface of the ocean, the hydraulic pressure exerts a constant crushing force of 10 kilograms per square centimeter against the structural walls. Why is such immense geological pressure not enough to collapse these man-made arteries? The answer lies in the engineering transition from land to the seabed, where Japan has established itself as a global leader in subterranean construction. But this is just the beginning of the technical challenge. Undersea constructions now connect fragmented islands and span deep bays where traditional bridges or ferries have become obsolete. At first glance, the task of connecting coastal regions seems straightforward, yet the reality involves overcoming a completely isolated environment where geological conditions shift with every meter of progress. It gets more complex further on as these tunnels transform into vital economic arteries, ensuring a steady flow of goods that is no longer dependent on surface weather conditions. One can notice how the first phase begins with comprehensive seabed surveys of the subsea topography. Engineers collect soil samples and analyze rock strata to determine the bearing stability of the seabed and identify latent hazards. Why are these surveys conducted with such exhaustive detail? Soil instability could lead to a catastrophic shift during the placement of structural segments, meaning every millimeter of rock density must be accounted for before a single machine is deployed. The project team must assess the potential impacts on marine ecosystems while simultaneously ensuring technical feasibility. Environmental considerations are prioritized through the implementation of noise mitigation measures and the installation of artificial reef structures to offset habitat disturbance. The process is only gaining momentum once the data is verified. 73,000 tons is the weight of a single reinforced concrete segment used in the immersed tube method. Each of these massive elements measures approximately 217 meters in length and is prefabricated on land with jewelry-like precision. It is visible how the segments are divided into several functional compartments, including 2 main chambers for highway lanes and 1 dedicated railway line. This design ensures that the tunnel can serve multiple transport roles within a single footprint. Floating pontoons and specialized cranes are used to lower these segments into pre-dredged positions on the seabed. This operation requires the equipment to move at a slow, controlled pace to maintain alignment despite the underwater currents. It only looks obvious to lower the tubes into place, but in reality, the most critical phase lies in the joint connections where seawater infiltration is a constant threat. Rubber gaskets are inserted between the segments to establish a watertight seal against the external pressure. To counteract the natural buoyancy caused by the surrounding water, layers of sand and gravel are placed above and around the structure. The camera glides along the length of the tunnel as the temporary end bulkheads are removed, transforming the individual tubes into a seamless, unified passageway. However, this specific technique is only suitable for regions with stable seabeds and gentle currents. Everything only gets more complicated when dealing with strong turbulence or complex underwater terrain. In such environments, the immersed tube method becomes impractical due to the difficulty of anchoring the sections and maintaining waterproof integrity. After the structural assembly is finalized, the phase of safety inspection and operational assessment begins immediately. 2 levels are often designed into these modern tunnels to double the traffic capacity without expanding the outer structural footprint. Drivers maintain a stable speed of 60 kilometers per hour while passing emergency exits positioned every 200 meters. One can notice how engineers carry out rigorous tests on the heating, ventilation performance, and overall structural stability of the interior. The process does not end at this stage of completion. Hundreds of sensors installed along the inner lining continuously monitor pressure, temperature, humidity, and vibration. This real-time data is transmitted to a central control room where engineers analyze the earliest signs of structural fatigue. Technical teams conduct regular inspections of the concrete lining and the drainage systems to ensure no deformation occurs over time. Specialized vehicles equipped with high-pressure water jets and suction systems remove sediment and debris from the tunnel floor. This combination of advanced sensor technology and manual maintenance routines allows the structure to operate for many decades. The tunnel remains a physical testament to human engineering resilience against the harsh environment of the ocean depths. Thus ends one of the most complex chapters in modern infrastructure development. 1,000 kilometers of coastline serve as the foundation for Japan's most complex ocean-facing megastructures. Why does a nation invest such immense resources into these massive concrete and steel barriers? At first glance, the construction of a tsunami seawall appears to be a straightforward defensive measure, but in reality, it is a sophisticated system of energy dissipation that protects millions of lives. The process is only gaining momentum. One can notice how massive concrete blocks, weighing several dozen tons each, are positioned with centimeter-level accuracy by specialized maritime cranes. The equipment gradually lowers these structures into the surf zone, where they lock together to break the force of incoming waves. Tunnels are bored hundreds of meters beneath the seabed using massive shield machines. These mechanical giants grind through solid rock and soft sediment while simultaneously installing reinforced concrete segments to line the passage. It gets more complex further on. Engineers must maintain precise pressure balance to prevent the intrusion of seawater into the workspace. It only looks obvious to connect islands, but in reality, the geological pressure at these depths requires constant monitoring by automated sensors. One can notice the camera gliding along the smooth reinforced arches of these undersea arteries, which withstand the immense weight of the ocean above. Everything only gets more complicated as these projects move from the design phase to physical realization. Such engineering achievements demonstrate the technical capabilities of a country that consistently reconstructs its infrastructure after every natural trial. Japan's advanced engineering and the systematic resilience of the nation allow for the successful completion of these incredibly difficult mega-projects. Transition to the next level. Other global regions also implement unique large-scale structures to solve complex logistical and environmental challenges. From here, the transformation moves to the next phase of processing as global industrial expertise continues to evolve. Thus ends one of the key stages of exploring maritime engineering.